ZeroCast number 4 here from ZeroCast World Headquarters. I'm Scott Harden, VP of Global Marketing. I'm glad all of you could make time to join us again. We're excited to share with you another fun-filled day of information and knowledge about the products that we're so passionate about. We're very fortunate today to have Biffard, our Director of Powertrain Engineering, here with us. Brian's been with the company for a number of years and is directly responsible for the magic that's gone into those power plants that are in our bike. I think you're going to find the presentation today very educational and fun at the same time. Got a lot of cool content to share with you. So without any further ado, I'll turn it over to Brian. Brian?
Thanks, Scott. Hello, everyone, and welcome to ZeroCast number 4. As Scott mentioned, my name is Brian Biffard. I'm the Director of Powertrain Engineering here at the Zero Motorcycles. Have been here for it's about 5 years now. So let's get into the presentation here. So here's the agenda. I'm just going to give you a little bit about my background, go into a little bit about electric motors and what exactly an electric motor is and what the benefits of an electric motor are. Go through a few different designs, different kind of architectures for the motors, and then we'll talk about what inspired the Z-Force motors that we have in our motorcycles today. Talk about the performance and then the new additions to the design for 2016, in particular the IPM and what advantages it brings. And then at the end we'll have a Q&A. So during my presentation here, feel free to add comments. I actually encourage you to comment on what I'm talking about, and at the end, we'll have a moderator who will feed me those questions, and I'll do my best to answer them. So, so let's get in here. Here I am. That's me at my house in Canada. I grew up in Kelowna. I raced BMX bicycles when I was a kid. I was passionate about two wheels. I purchased my first dirt bike when I was 8. It was a 1973 Honda XL 75. I really liked the 4-stroke because it needed to be quiet in the areas that I wanted to ride, and still what I'm passionate about, having nice, quiet enjoyment of the outdoors. Skipping ahead quite a bit, I was at the University of Calgary Solar Car team for 2005 through 2009, where I was the manager of the electrical team. On that vehicle, it was a very high efficient motor, but the downsides of the motor were extremely heavy, very costly, and unreliable as well. So I thought I should start learning about electric motors so I can design a better one, and that eventually brought me here through direct drive wind generators design from 2009 through 2011, and then here at Zero Motorcycles since 2011. So yeah, first I'm going to talk about the electric motors here. So 99% of electric motors work based on magnetism. So you might want to think, some people might wonder why 99% of motors. There's one particular motor that actually works based on the thermal properties of electricity, and it makes something hot and it makes it spin rather than magnetism. But I just put that 99% in there so that those of you who wanted to poke holes into this thing here would know that, yeah, there are some electric motors that actually use heat rather than magnetism. But the main kind of motors are DC brushed motors, PMAC, which is permanent magnet alternating current motors, and AC motors. Here I've got a link to a YouTube video from the Air Force 1969. It's a really interesting film. I recommend everybody go after this presentation, go and watch it. It's fun to see what people thought about motors in 1969, and it's really informative. There's quite a few good videos there, and you'll see a few more in the next slides. So what is an electric motor? An electric motor is a torque device, and the torque is what really drives you. It's interesting, quite a few people will get on a really powerful internal combustion engine motorcycle and say, when it gets off the line, they say, wow, this really accelerates quickly. It feels electric. And now we're actually making electric motorcycles that people get on it and they say, yeah, this feels electric, and they get excited by it, and it actually is electric. So an electric motor produces torque, and that torque is related to the current delivered into the motor. So if you have a particular motor, if you get a certain amount of torque out of it at say 10 amps, you'll get twice that torque out at 20 amps approximately. There's at the end of the range there's nonlinearity, but overall, if you have a motor, you double the torque, you have to double the current. Unfortunately, that current produces heat. The more current the heat actually goes up with the square of the current that goes in. So you double the torque, you produce 4 times the heat. And that maximum temperature is where you actually determine how much torque can your motor produce continuously. And that it comes down to how much heat can you remove from the motor, and that defines how much continuous torque you can produce. So here are the different kinds of electric motors. The first one I want to talk about is the DC motor. It's a really old design. It's still a lot of motors, like slot car race cars, and a lot of different applications still use the DC brushed motor. They have a number of advantages. They're really simple, they're really easy to control, and they're extremely inexpensive. There's a few different kinds of DC motors. You can have permanent magnet motors or electrically excited. All of the DC motors have brushes, and the brushes wear out. They take up quite a bit of space. And the other thing that all DC motors have in common is they have rotating copper coils. And those copper coils are soft metal material, and as you spin them faster, it becomes more difficult to contain the copper from bending, going where you don't want it to go. So here's a PMAC motor. So this is sort of an evolution in the motor design, where you take the permanent magnets, and instead of holding permanent magnets stationary and having moving coils, you hold your coils stationary and you rotate your magnets. The advantage of this is that there's no more brushes and no wear parts other than the bearings. But the challenge with it is that you've got more complicated control, and you require precise position information to be able to control it well. So down there at the bottom of the slide, you can see that it's sort of showing how the north poles of the stator. So the north pole there is the blue stator tooth is a north pole, and it's in that first slide. It's attracting the red magnet on the rotor towards itself, and it's pushing the blue magnet away from itself. Then as you move to the next slide, you can see how the north pole has been moved a little bit by changing the magnetic, or by changing the current in the coils. It's moved the north pole clockwise around through the rotation of the stator's in one spot, but the magnetic field moves within the stator, and that pulls the rotor around to continue the rotation in a nice continuous motion. All right, so now the other motor that I didn't talk about here is the AC motor. It's probably the most common motor, but it's left it out of this presentation because you can go online and find all you want about AC motors. I actually imagine most of you already know everything you want to know about AC induction motors. So what I want to move on to now is why did we want to build our own motor? And so it comes down to we were working with third-party motors from 2009 through 2012, different brushed motors and brushless motors. And we realized that by making our own design, we could meet the design goals specific to our electric motorcycle. And so here's a list of what our particular goals were. We wanted to have good acceleration, which translates to impressive torque, and a broad power band. So we wanted to impress the rider and have a very good rider experience, and have high performance vehicles. We had extremely compact space constraints. Being a motorcycle, we wanted to package as big a motor as we possibly could in the space that we were provided to provide the highest power highest continuous power and the best heat dissipation. We also wanted to make sure that there was no maintenance required on the motor. And going with our mantra of sophisticated simplicity, we wanted to do our best to make sure that our motor didn't require any complicated cooling systems. And to do that, we wanted to have just passively air-cooled, no fans, just let the air flow past the motor and make sure that that's sufficient to deliver the continuous power and continuous speeds that our customers are expecting with our motorcycles. Also, again, with the sophisticated simplicity, we wanted to keep it as simple as possible, have no gearbox or transmission. Those are just extra spinning parts, and if you can design a system to not require them, it's much better. So here we are, the key considerations for why we decided to go with the motor architecture that we did. So on a motorcycle, you're very space constrained, and so we wanted to go with the highest power density we possibly could. So in 2013, that was a permanent magnet alternating current motor with surface-mounted magnets. That's really your best bet for trying to get the most power into the smallest package. The other thing that was a consideration was to go with simplicity, was to get our air cooling. We wanted to maximize motor efficiency. And essentially what that means is that the more efficient a motor is, the less heat it produces at a given power. And so the less heat that it's producing, the lower the temperature is required to get rid of that heat. And so we want to be able to have a very low heat production so that we can simply use simple air cooling and not have to rely on other systems to get the heat to places where we can effectively get rid of it. And then here we're, again, through our whole system, if you can design a motorcycle to give you the acceleration that you need at low speed and still maintain and get to the desired top speed without the use of a transmission, you can improve the efficiency of the overall system without sacrificing rider experience. So yeah, as you can see there, we designed the RPM, the maximum RPM of the motor was based on our available gearing and the desire to have 100-mile-an-hour top speed. So here's sort of the result of our development. You can see going through the years, we've got 2009, we're producing around 12 horsepower. Just follow the major trend of those graphs down at the bottom there. Horsepower almost doubled when we went into 2010, 2011. We moved to a brushless motor for the SDS motorcycles in 2012. We also got another noticeable improvement in power, going from around 22 to 28 horsepower. And then when we introduced our 2013 product line, we almost doubled the horsepower up to just over 50 horsepower. And since then, we've introduced the SR platform that just now has over 60 horsepower. And you can see at the same time we were able to increase torque. And that allowed us to get good acceleration at low speed while increasing the top speed of the vehicle. This slide here shows a typical torque and power graph for the motor. As I mentioned earlier, a motor is a torque device, and so the torque is proportional to the amount of heat that can be dissipated is related to the torque that's produced. And so if you have a certain amount of heat that you can get rid of, why don't you just keep on increasing the speed while producing the same amount of torque, and you'll just get more and more power out. Electric motors produce a back EMF, which makes that at higher speed. Go back a slide again. As you get into higher speed, it becomes more difficult to put the current into the motor with your battery voltage, and so you can't just increase speed to give more power. There's a point at which the torque is limited due to the battery voltage. Okay, so next slide. So here for the, model year 2016, we had some new developments, which was primarily the interior permanent magnet designer, IPM. So we've got some patent pending on this. I'll talk about those a little bit later. It's electromagnetically and structurally optimized for performance. So performance is mechanically and electrically. So we wanted to make sure that that the motor was able to tolerate higher temperatures and produce less heat at the same time. So that allows us to increase the continuous top speed of the vehicles, and at the same time we were able to reduce the complexity of the motor. So I'll go into the specific design here on the next slide. So this slide here is an animation. So hopefully it gets through to you viewers out there. Shows that the parts that came out there is the encoder at the left side of the screen, and the rotor comes out of the front. So you can see the number of components inside the electric motor is fairly minimal. It's just the stator, the rotor, the motor case, some end plates, and then all the rest of the stuff is really just bearings. So here again, the encoder, which tells the rotor position. It's a little magnetic and Hall effect sensor that tells the motor controller exactly where the rotor is. That's the rotor that came out. And inside this case, there's the stator. So yeah, if you guys have questions about what the different components are, you can bring it back and we'll bring it back to this slide. Okay, so yeah, if you just want to pause it for a second here, Sean. This animation that's going on shows the surface mount permanent magnet motor design that we were working with from 2013. So around the outside of the circle here, that's the stator, and the stator iron is modeled here. You can see the pink lines there show, or sorry, the color gradient shows the magnetic field density, and so you can see there's the iron is where the magnetic field is transfers from one magnet through to the next, and right there, the surface of the rotor, or just inside the stator that we're pointing at here, is the magnets, and so the magnet there is, each magnet there is a pole. And so it would be a north pole on one, and the following one would be a south, and you create a magnetic loop that goes through the stator. What I wanted to highlight in this animation is the change in magnetic field density inside the magnets. So you can see as the magnet travels around, it has a higher magnetic field density when it's adjacent to the stator teeth. When the magnet is adjacent to the gap between the stator teeth, you can see the magnetic field density goes to a light blue color, and that's indicating that it's a much lower magnetic field density. You can look at the side there. I think it's 0.6 Tesla at blue and 1.6 Tesla at pink. And so change in magnetic field density in a conductive material means the production of electric current. And whenever you have electric currents that are being produced inside a conductor, that means you've got heat being produced. And so what the surface mount motor design produces is quite a bit of eddy currents going on inside the magnets that are undesirable. It heats the magnets up, and the magnets are the most temperature sensitive component inside the motor. So you really don't want heat production, but the benefit of the surface mount motor design is that you really do get the highest flux densities in the stator, and you can get a really high power dense motor using surface mounted magnets. So yeah, if you guys have questions about this, feel free to ask them, and I'll come back to this slide later. But now we'll move to the interior permanent magnet motor. So we'll just pause it there. So the biggest difference here I should start with the similarities. So the stator on the outside there is exactly the same as it was from the surface mount motor got the same number of slots in the stator. The big difference is in the rotor, obviously. So you've got there, the rotor iron has got material on both the inside and the outside of the magnets, which trap the magnet inside the rotor. So what that allows is for easier manufacturing. You don't have to worry about gluing magnets onto the surface of the motor. You can just slide them into these slots. But the other thing that it does is it makes the magnetic field more uniform throughout the rotation of the motor inside the magnet. So you can see the magnets now are pretty much staying a constant orange to purple color. And there's no areas where you have large magnetic field changes inside the magnet. So that reduces the eddy currents produced in the magnets, keeping the magnets at a lower temperature and producing less heat overall to get rid of. So that allows you to have a higher continuous output power, but also allows you to operate the motor at higher temperature because the magnets are not producing heat, so you don't need to be so cautious about overheating the magnets related to the temperature difference between the stator and the rotor magnets. All right, so what does that mean in terms of performance increase? So this is a graph showing our typical limit performance testing. So we here like to go to racetracks and test our motors. Their ability is something I've been fortunate to be able to take part in. This wasn't me riding. I was monitoring the data from the side of the track, but it was still a successful and fun day at the Thunderhill racetrack up in Northern California. So let's start looking at the blue line over on the, the axis along the bottom is time in seconds. So this was around 1,200 seconds, which is about just over 20 minutes, I think. I don't know, I guess 15 minutes of testing. The blue line shows the motor temperature. So you can see when the riders started riding pretty clearly at around 100 seconds, they got on throttle and did a nice warm-up lap. Then they got into second lap, and you can see as the temperature drops, it's probably in an area, a slower section of the racetrack, and so you can see the different laps that the rider took. And you can see on his third lap, I've highlighted the top there where you have motor temperature cutback zone. So once the motor temperature reaches the bottom section of that, or enters into that zone, you'll start experiencing torque reductions to make sure that your motor doesn't go over the desired temperature. So this is what we call the motor thermal strategy. So there on about the third lap, the rider would have experienced very slight motor thermal strategy torque reductions, but they probably wouldn't have even perceived the reduction at that point. On the next lap, they were approximately 10 Celsius into the motor thermal strategy. And I'll show you what that actually meant in terms of lap time and top speed later. But the other thing I'd like to point out right now is that red line that goes right across horizontally at around 105 Celsius. That's where the surface mount motor would have started entering into torque limiting mode, just to protect the magnets of the surface mount motor. So we've been able to achieve a significantly higher temperatures for short periods of time with the interior permanent magnet motors. Next thing I want, so related to speed, you can see as you can see the dips there kind of show the different laps. So you can see his first warm-up lap, and then he got into lap number 1. He reached a top speed of just over 100 miles an hour. He was still able to achieve the same top speeds for laps 2 and 3 and 4. And then on lap 5, he started to experience a small amount of top speed limitation due to the thermal limitations of the vehicle. But it sort of just continued on at the same thermal limitations for the next few laps. So it's sort of what you would call reaching equilibrium, where the cutbacks that the vehicle is taking to protect itself are balanced, and no more additional heat is being produced which would require further cutbacks. So Sean, if you go back one slide, what we've got, the next thing here that I wanted to show you is how balanced the system is. So the electric motor does get into its motor cutback range right at around lap 3. Right at lap 4, you can see I've drawn in a controller temperature cutback range just above 70 Celsius, between 70 to 80 Celsius. And the motor controller is reaching its thermal limitations right very shortly after the motor did. And then if you continue down and look at the green line, it enters a battery temperature limitation, because we're pushing the battery about as hard as it could for this session. And so you can see that all of our components are achieving their maximum performance at around the same time. So that shows that it's a nice, well-balanced system. We're extracting as much power from all of the different components at the same time. All right, so here's just a little bit of technology stuff. Back in 2013, the biggest thing that we needed to do was make sure our motor was small. So we worked with Micah, and the motor has been a real team project. So in 2013, one of the key contributors was Micah, and we came up with this neat system that allowed us an inexpensive and robust way of getting the current into the motor with using a small amount of space through the way that we clamp the phase leads on the back of the motor. And then in 2016, we had the major step forward with the IPM design. One of the big, or I guess a few of the difficulties with the IPM design is to be able to use about the same amount of magnetic material. Magnetic material is quite expensive, so you want to make sure that you don't use more than you need to. At the same time, when you work with your magnets inside the rotor, it makes the rotor typically heavier because of the more iron that's required to have the structure to hold the magnets. So we focused on minimizing the support structure that's required to hold that iron in place. So you can see we have the nice little spoked structure to the hub, and we've got a patent pending on that. And again, it was a team effort, and it was really interesting to see all the input from the different team members of here at Zero Motorcycles, and I think we've come up with a pretty neat looking and very effective design for enabling us to have an IPM motor that has the same output performance as our surface mount motor and still has the same weight and better thermal properties, which allow us to increase our continuous operating speed. All right, so that comes to the end of the presentation mode, so we'll go back to showing the camera, and open the floor. The moderators here will read me some questions, and so yeah, please start commenting if you haven't already, and let me know what you think of my presentation, and let me know if you've got any questions.
All right, and there's going to be a little bit of a delay between when people ask and when they see an answer. Yeah. So we'll get started with some of the early questions. First question we had was from earlier in the presentation, and it was, why are the cooling ribs not in the riding direction? Doesn't that provide more airflow?
Yeah, so that's actually a very common question. Is the airflow under the motorcycle, you'd expect it to go from front wheel towards the back, and you actually you'd want the fins to be able to optimize for that airflow. And if you do that, the motor case is an extrusion, or it's very easy to make an extruded motor case, and so extrusions lend to have axial features, and it makes it so that the fins are in the axial direction because of the extrusion. And we actually did quite a bit of measuring of the using tufts of yarn and different techniques to be able to model the airflow around the motor. And sure, on the bottom of the motor, there's quite a bit of airflow from the front to the back, but almost everywhere else in the motor, it's almost random in the direction that the airflow has. So saving money on the case and making it a simple tool was optimized for our vehicle, and we're trying to bring a low-cost product to our customers, and having axial fans wasn't a big detractor from the performance of the vehicle.
Okay, that question was from, I'm going to mispronounce this for sure, Krieg G. Neat. Sorry for the mispronunciation. Got another question here from Dr. Bass. Ryan, you mentioned the Hall sensor. Is the motor no longer using the sin cosine encoder?
No, we still use the sine cosine encoder, and it works well. And it's a Hall effect sensor that has an output of sine and cosine. So I know a lot of you from the endless sphere community. When you say Hall effect sensor, you think of the three Hall effect independent Hall effect sensors, and in the industry that's called UVW encoder, and that one gives you a position, an absolute position information every 20 degrees rotation electrically. And with the sine cosine, you get a much more precise information particularly at low speed, and you can have smoother starts with the sine cosine sensor rather than UVW, or what's commonly known as Hall effect position information.
All right, our next question is from Simone Rambaldi. Again, sorry for the mispronunciation. So SMPM have higher flux but higher heat generation.
That's correct. Yeah. So one thing we did with I didn't mention during the presentation, the SMPM motor, to reduce the amount of eddy currents produced in the magnets themselves, we may use very small magnets, and there was over 200 magnets inside each motor to break up those eddy currents. So if you have a large conductor, you get more eddy currents being produced inside it. So by making small magnet sections, and they were coated in epoxy so that they weren't conductive to each other, we were able to reduce the eddy currents inside the magnets as much as possible, but it did make the assembly more complicated by having a larger number of small magnets.
Okay, we got another question from John Marshall. Looks like you played with the tooth gap between the surface and IPM designs as well.
Oh, yeah. That's just in the model that I showed you. I figured some people might go through and do screen captures and try and get the latest and greatest information from the screen. So that was an older version of the stator. I didn't want to have the most recent versions of stuff. So there actually is no difference between the SMPM stator and the IPM stator. But good eye catching that.
Okay. Let's see, we got another one. So John Rushworth says, IPM is a great advance on the surface-mounted magnets. Good explanation.
Thank you.
Okay. Here's one from Simone Ribaldi. Can you still use the oil trick on IPM?
Yeah. If you put a liquid-cooled motor, you can improve the performance of that. At Zero Motorcycles, we're focused on sophisticated simplicity, and for our customers, the best solution is a simple solution. So that's what we're going with. You can get better performance out of a motor by adding complex cooling systems to it.
We've got a question from Kurt Ringer. Would it be possible to get a copy of this presentation? And I'll just jump in on that one. That is available on our live stream channel later on, so you can rewatch this. Yeah,
so you can watch it, and also there should be links on the live stream channel to those informational videos from the U.S. Air Force that I found entertaining and enlightening.
And Troy Rank sent in a word, ferrofluid, ?
Yeah, so those of you on the forums may be aware of, what's his name up in Canada, but at Grin Technologies, Justin Lee, yeah. He's got this neat little product, he calls it Statorade. It's a ferrofluid that he can stick inside his motor, and the magnets put this stuff right around the outside of the stator, and or right around the outside of the rotor, and it assists with the heat transfer between the rotor and the stator, and It also has a side effect of effectively reducing the air gap, which means your motor may produce more torque with this small bit of material in there. So it's an interesting thing, and we're always looking for new innovations and things, the way that we can improve our product while still maintaining the sophisticated simplicity mantra of the company. So yeah, we're looking into neat techniques and technologies like the ferrofluid to see what they can do.
We have a question from John Marshall. I see the end rings on the rotor. Is that an opportunity for weight savings?
The end rings on the rotor are made out of aluminum. They have a small lip on the ring around the outside. It's one of the differences between our surface mount motor and our IPM motor, one of the new advantages that I didn't highlight. We moved to an aluminum end plate on the rotor, and it doesn't add a significant amount of weight, but what it does do is it provides our motor manufacturer with the ability to remove select material using a drill to remove weight to balance the rotor. Instead of with the SMPM motor you had to add bits of weighted epoxy to balance the rotor. And so it makes the manufacturing process simpler and more consistent.
We have a question from a gentleman named Jeff Jolin, which is about the future, which we don't usually get into details on, which is how much horsepower do you see in the future with the IPM motor?
That's a tough question to answer. With the specific motor that we have, we're starting to push the limits of the motor's technology. Right, we designed the whole system to work well together. So that was with the motor controller and the battery and the motor. So it's all fairly well balanced. So you'll have to wait and see what we get. But yeah, you're not going to get 200 or 300 horsepower out of our motor because it was designed to be the motor for our motorcycle.
And this is a little bit of a follow-up to the power question. Again, this one's from John Rushworth. Thanks, Ryan. To increase power further, would you have to go to liquid cooling?
Not necessarily. Liquid cooling is one way to get rid of the heat, but actually liquid cooling really doesn't actually get rid of the heat. It just moves the heat into a place where you can get rid of it more easily, right? A radiator takes the heat from the engine or motor, transfers it up to a place where you've got good airflow. So if we can improve the airflow to the motor, that would be one way of increasing the continuous power. Another thing that you could do to actually increase the continuous speed would be aerodynamics. So yeah, there's a number of ways to improve the product to be able to get more continuous power out of the vehicle.
We have another question from Mr. Jeff Jolin. What is the top RPM you have reached with the IPM in testing?
It's a good question. We've gone well over 6,000 RPM, which is what our motorcycles are limited to 6,000 RPM on the street. We've tested above that, but due to homologation of brakes and such, you can't go faster than what our homologated speeds are. So yeah, we know that it takes quite a bit more than 6,000 RPM to get our motors to stop functioning properly.
Dr. Bay says, thanks, Ryan, for the first answer. We have a question from John Marshall. Any development on the stator improved fill to improve efficiency? Right.
So that's another thing that can be done to improve the power. As what was it? One person asked if liquid cooling could be used to improve the performance. The other thing is, right, liquid cooling allows you to get rid of more heat if you can get that heat to some place to get rid of it. The other way to increase power is to produce less heat. So that's what we've done for using the IPM. It produces less heat. As you said, on the stator, if you can get more copper in there, you can reduce the amount of heat produced. And that's a way that could improve it. Right now, we're pretty happy with the way that the winding is done at our manufacturer, and I can't get any more copper in there using the technique. So we're going to have to come up with interesting ideas, and if you have some interesting ideas of how you can get more copper in there, I'd be happy to hear them. So, yeah.
Laws Nanigans says, cheers for the presentation, guys. Look forward to riding one.
Yeah, if you haven't been on one, yeah, what's your holdup? Get on one. They're everywhere.
Thank you, Laws. Kurt Ringer, is the IPM being used in just the 75.7s or the 75.5 also?
It's being used in both. So the FXS for 2016 has the 75.5 IPM, and the SR and SDS have the IPM 75.7s in them.
From Arlen Sansoni, what's the max RPM going to be of the IPM motor?
As this question was asked already, so yeah, it's we're limiting the maximum RPM to 6,000, and we're confident that there's not going to be any issues with that speed.
All right. From Joe Rescott, how much is this new motor expected to improve the bike performance in terms of acceleration, sustained speed, motor efficiency, and/or range?
Right. So I'll try and answer all those while they're fresh in my mind. So the acceleration is still the same. The motor doesn't produce any more torque than it did before, and we still have the same gear ratio. So the acceleration is the same. The top speed is the same because we've also limiting the maximum motor speed to 6,000 RPM, which was the limit for the SMPM motor. Continuous power, continuous top speed was improved just because of the efficiency improvements. But actually, the range is a complicated thing. There's a lot of sources of loss inside the powertrain. You've got losses in the battery, losses in the cabling between the battery and the motor, losses in the motor controller, losses in the motor, losses in the belt drive, the tire, and your major source of loss, which is aerodynamics. So overall, the amount of loss that's produced by the motor is relatively small. So improving the efficiency of the motor is not really something that will see huge benefits to range, but it does provide a benefit because you can use slightly less power to continue at the same speed. Instead of having maybe 500 watts of loss in the motor at a speed, you might go down to 470 watts of loss. So that's saving you 30 watts, about the same as turning off your headlight or something like that.
Okay, we've got a question from Giuseppe. It's actually about the charge tank. Normally we wouldn't have other questions about other topics, but I'll allow this one because I think it's a pretty straightforward one. Mm-hmm. If you can't answer it, that's fine, right? The charge tank will charge the bike at 16 amp single phase, or is there a possibility to go up to 32 amp single phase? No,
the charge tank is it's output limited. So regardless of what power source you provide to the charge tank, it'll always output like 2.5 kilowatts. So whether and there is no three-phase input to it. So it's either 110 volts or 240, 220 volts in there, single or dual phase.
Okay, moving on. Samuel Brunau, can you say how much the motor weighs?
Yeah, it's our 75.5 is around 30 pounds and 75.7 is around 38 pounds. Or 14 kilos and 17 kilos.
Okay, from Jackson Edwards, any developments with the IPM at higher frequencies, or is the controller going to continue to be a limiting factor?
Yeah, so as I mentioned earlier, right now we're limiting our top speed to 6,000 RPM. We have experimented with going faster, and we know that's something that might be possible in the future, but due to limitations at the time, we don't really foresee that.
From Curtis Waterford, how long can you sustain a 70 mile per hour speed before thermal limiting?
Indefinitely. At 70 miles an hour on a flat road with regular ambient temperature, 25 Celsius to 35 Celsius, you can go 70 miles an hour tucked or untucked as long as your battery has power. So on a typical S with approximately 12 kilowatt hours, going 70 miles an hour takes about 10 kilowatts, so you can go around 80 miles at 70 miles an hour.
Okay, question from John Rushworth. Can you explain field weakening in relation to RPM, as I primarily understand DC brushed?
Okay, so if we go back to the presentation, I can show you on the torque slide. There we go. So yeah, essentially, field weakening is a trick that you can use for brushless or PMAC, and what it does is it allows you to go past what's called your base speed. Keep going back to the torque graph. The base speed is the speed at which the back EMF from the motor is equal to the back EMF from the motor is equal to the battery voltage. And so in this graph here, you reach base speed at that torque at around between 3,000 RPM and 4,000 RPM, and that's where the torque starts dropping off. So with a DC brushed motor, that torque curve would just drop off very dramatically. But by using field weakening, which is essentially in DC brush world, it's called timing advance. Some people have come up with neat ways of mechanically altering the timing, moving the brushes, how they commutate, and it allows you to spin faster by rotating the brushes. Essentially, field weakening is the digital equivalent to that, and it allows you to adjust the time at which the current is going into the phases, and allows you to trick a little bit more power out of the motor. And actually what you have on this graph here is a constant torque range, which is 3,000 RPM and below, and then above that is what's called the constant power range, which is 3,000 RPM up to around 6,000 RPM. And so one term that's used is the constant torque to constant power ratio. And that's one of the key things to consider when you're designing the windings of a motor to match the battery voltage and your motor controller. And so here we have a constant torque to constant power range of around 1 to 1 or 1/2, depends on who you're talking to. But yeah, so we designed that so that you get constant torque all the way up till about highway speeds. And then once you are at highway speeds and above, you're in your constant power. So when you go wide open throttle, you've got about, in this example, or in this SR here, you've got about 60 horsepower or more on tap, as soon as you're around 3,000 RPM. Below that, you're torque limited.
Okay, we have a question from Alex Rommelfinger. On the topic of improving heat removal from the engine, have you done any testing of aerodynamics packages to route airflow across the fins on the case?
Yeah, so if you look at the difference between, I think it was in 2014, we introduced a plastic skid pan on our S platform. If you look closely, you'll see a few little deflectors, kind of like you'd have on the underbody of a Formula One car, that help direct the airflow up towards the motor. Also, the side fairings that cover over the battery have a few little holes in them to help direct the airflow to the motor as well. So yeah, CFD is a very complicated thing, and trying to get airflow to the motor is sometimes more difficult than you might think.
So a question from Noah Davis. Why are the freestyle moto guys not using these lightweight, torquey rigs? One
thing is I don't think we've been introduced to any freestyle moto guys, but I know a lot of the extreme freestyle guys doing significant tricks. The engine actually plays quite a large part of the feel of the motorcycle when it's in the air. So it would probably take a little while for them to get used to the difference in the electric powertrain. And I'm excited to see what they can do with our bikes once they get on them.
All right, so a question from Dr. Bass. So if actual 6 kRPM is for max speed brake are approved for, is it possible to increase over 6 kRPM and change gear ratio to boost HP and keep same max speed?
Right, so if we did that, going back to the graph that I just showed you, it would shift the whole graph down at lower speeds. So you would start getting into your field weakening at lower speeds, and what that means is you're starting to get into lower efficiencies at your cruising speeds, and that would be somewhat detrimental to range or perhaps heat production. So That would be something that's possible, but the other thing is that right now, if you look at our motorcycles, there's a really large rear sprocket and a really small front sprocket, and we designed the motor to reach 6,000 RPM, which is about as fast as we could spin while going 100 miles an hour, and using the largest gear ratio we could on the vehicle without having the sprockets be too small at the front, which reduces belt life, or too large at the rear, which they may get hung up when doing trail riding and things like that.
Okay, we have a question from Andrew Kramer. Voltage rating. What is volts peak to peak and RMS rating of the windings? Is it possible to up the voltage of the system to help reduce heat by lowering the current?
Right. So if we use the same motor as we have today, the same stator, and just increase the voltage, what that would do is it would increase the base speed. But because, as we said, because of the gear ratio, even if we could spin faster than 6,000 RPM, we wouldn't be able to use this speed, because you would end up with either going too fast or getting into a situation that just is not optimal. So the motor, a motor doesn't really have a voltage peak to peak rating. Our motors are tested at the manufacturer. They're tested to 1.5 kilovolts for isolation. We have no problem supporting higher voltage, but there's really no advantage to going higher voltage with the rest of our system.
And Andrew followed that up with a second question, which is, would it help to not generate the heat in the first place?
That's so. If, as I mentioned at the beginning of the presentation, a motor is a torque device. So if you're trying to get the same amount of torque out of a motor, regardless of the system voltage, it depends on the amount of current into the motor. So if you designed your system for higher speed and higher voltage, then you would be able to use less current to get the same amount of torque, but it would still produce the same amount of heat. So torque equals heat, regardless of voltage.
Okay, question from Emilio Bola. How and where do you measure the motor temperature? Why the motor is active while charging the motorcycle?
Okay, so the motor temperature sensor is buried inside the stator coils. So it's the coils are usually the hottest component of the motor, and it's virtually impossible to actually measure the rotor temperature with a cost-effective solution. So yeah, our temperature sensor is buried right inside the stator, right at what we feel is the warmest point, to make sure that if the temperature sensor is reading a temperature, it's accurate for the overall motor. What was the second part of his question?
I think it was, why is the motor active while charging the motorcycle? Right.
So it's based on the algorithms that we have in our motorcycle, is that if the motor controller, for whatever reason, decides that it is not safe to have the contactor closed, the contactor will open. So during charging, the contactor needs to be closed, and the motor controller is the thing that decides, is one of the components in our system that we have to listen to decide whether the contactor is closed. And so the motor controller must be on to tell us that it's safe to keep the contactor closed at that time. And determining whether it's safe it's a system level decision that comes from multiple components.
Okay, we've got another question from John Rushworth, which is a little bit outside of motor design. It seems to me that you have designed a very balanced system, and the biggest gain could be in aerodynamics. And again, future looking, are you looking into this?
I guess it depends on what you say biggest gains. In range, obviously aerodynamics play a huge, major source of loss. So improving aerodynamics would be a major benefit to range. But there's a lot of costs associated with aerodynamic benefits, and including just the amount of effort going into simulating what those benefits would be. yeah, we're looking at all sorts of things to make our product better. And yeah, if you guys want to see aerodynamic features, let us know. And you know, the marketing guys are always keen on telling us engineers what we need to make for you.
And then another question related to something slightly outside the motor area from Mr. 559797.
Easy to pronounce that one.
Yeah, that's true. We got that going for us. So, while I see no need for a transmission, there could be a need for a clutch, especially on a dirt bike. Any thoughts on this for the future?
A mechanical clutch is not a simple device, and our mantra is sophisticated simplicity. So for us to go to a mechanical clutch would be a big decision, and we'd need a lot of input from our customers to say this is something that we absolutely must have. There's interesting ways that maybe we'd be able to use throttle control to give a rider the similar ability to have that they have with a clutch. So we're looking at always making our product better, and if customers say that they like the feel of a particular motorcycle or the way that the particular component on a motorcycle works, we can try and integrate that into our future products.
So we have comments from Rob Morgan and Ben Swing Ridge to the effect of more aerodynamics and more body styles. So always something to consider. So we see that. Another question from Simone Ribaldi. Have you already tested the motor with the new Gen 5 Sevcon?
The Gen 5 Sevcon that they've announced is the high voltage one, so it's a 300 volt system. So no, we haven't tested it with that.
All right, and I think that's about all the questions we're getting, and we're close to the end here.
All right.
Any closing remarks?
Closing remarks? No, thanks everybody for paying attention. Thanks for the great questions, and tell your friends to come and watch this in instant replay when they have some time. And yeah, make sure you go check out those entertaining and educational videos from the 1960s on motors.